triple integrals in cylindrical and spherical coordinates. Let me just review what happened with polar coordinates. Okay, when we dealt with polar coordinates, we said that we can convert from Cartesian to polar with these two equations. And what polar coordinates do is they take these rectangular coordinates and they specify a different way to identify points in space. So if I have this point, the rectangular coordinates would just be x comma y, and that's the distance in the x direction and the distance in the y direction. Polar coordinates specify this point by specifying an angle from the x-axis, that's called theta, and a distance from the origin, that's called r. So in polar coordinates, this point would be given coordinates r comma theta instead of x comma y. So you're given a distance and an angle, and that tells you where you are in space. And we can convert from Cartesian to polar using these formulas. So when we move into 3 dimensions, we're going to add another axis here, and we need to extend things out into that other dimension. All right, and so let's talk about the first way to do that is cylindrical coordinates. So cylindrical coordinates are probably the most basic way to do this. All we're going to do is we're just going to add that z coordinate into the mix. So really, it's almost doing nothing. So the relationships are the same for polar. We're going to do, oh, that's a sine theta, y equals r sine theta. And then how do I convert the z? Well, I just leave it the same. Okay, so in cylindrical coordinates, we just add the z variable to polar coordinates. That's all it is, polar coordinates plus the z. So how is that going to look in 3 dimensions? Well, I have my x, y, and z axes. I've got the setup for polar coordinates in the xy plane. So if I specify a point in space, what I'm going to do is I'm going to drop it down to the xy plane and look at that point down there. And then that point I can specify using this r and this theta. So r measures the distance that I am from the origin. Theta, as before, measures the angle from the positive x-axis. And then z is going to be this coordinate here, how high I am. The same z that we had in Cartesian coordinates before. All right, so the coordinates are going to be r, theta, z. And that's going to specify a point in space using these cylindrical coordinates. So we're going to specify how much we have to spin around in the xy plane, how far we have to go out, and then how high we have to go. And that will tell us where that point is. So we'll talk about the volume element. Well, recall what the area element was in polar coordinates. When we do an integral, a double integral, we write a dA at the end, right? So in 2D, we do a double integral over a region, and we have some function in here, and then we write dA. That's the area element, okay? And what that's representing is an infinitesimally small chunk of area. And the integral, what it does is it multiplies that by the function and then adds up all those values. So you end up getting, when you integrate a function like this, you end up getting the volume underneath the function because you're multiplying the height of the function times the area, and that gives you a volume under the function. But we need to talk about what this area element is, and we talked about that. If we imagine a small change in theta, so maybe I go from theta is this to theta is this. Right? That's not that small, but I have to expand it just so that we can kind of see it clearly. And then imagine a small change in r. So let's say we go from r equals here to r equals here. Again, not that small, but I need to draw it large so that we can see what we're talking about. Then what I get is I get a wedge, right? So the distance in this direction is what we call a small change in r, that's dr. And naively, you might first think, oh, well, then the distance in this direction is d theta. Well, that doesn't quite work because you'll notice it's different here than here. It's actually the distance in this direction depends on r. And we talked about how we have to use the formula for arc length to get this distance. And the formula for arc length is very simple. The length of an arc on a circle is just r times theta, if theta is measured in radians. And so since the distance here in theta, not the distance, but the amount of change in theta is d theta, I'm going to multiply r times d theta. And that's how I get this distance. That's r d theta. So this little chunk of area here, which we're calling dA, is approximately equal to this distance times this distance. So it's dr times r d theta. So dA is, and if you multiply that, you can put the r out front, is r dr d theta. That's usually how we write it. But you could write it r d theta dr. That's fine. But we usually write it this way, put the r's together. Right? And that's how we get our area element. So that's the area element. So we want to get the volume element for cylindrical coordinates. What are we going to do? Well, we're going to take this picture and we're just going to extend it into the third dimension. All right, and we're just going to add a dz to it. So what does that end up looking like? Well, so in 3D, for the cylindrical coordinates, this was for the polar coordinates. This was just polar. This will be cylindrical. All right, x, y, z. So the same picture. So what we did is we took a change in theta. We took a change in r, right? And that gave us this wedge shape down here. And now we'll just extend it into the z direction. So we'll just lift that up. And you get this wedge that's extended in the z direction. So now we have dr takes us this way. R d theta gets us that dimension. And then this is just simply dz. So if I want the volume, I just multiply. This times this gives me the area, multiplied by the height gives me the volume. So dv, this is the punchline here, it's going to be the product of all these. So I'm going to have r dr d theta dz. So that is what we're going to use when we do integrals in cylindrical coordinates. It's pretty straightforward extension of polar coordinates. We're just throwing the dz on the end. I need to tell you what the region is that we're integrating over. All right, so R is going to be the set of all points, x, y, z, such that x squared plus y squared is less than or equal to 9, x is greater than or equal to 0, y is greater than or equal to 0, and z is between 0 and 1. So what are we dealing with here? Well, when I see x squared plus y squared, I know that if this was x squared plus y squared equals 9, that would be the equation of a circle of radius 3, right? And that tells me right there that maybe cylindrical coordinates are the way to go, because cylindrical coordinates deal with, they're kind of circular in their nature. They have that angle as part of it, and so it's natural to write down circles in cylindrical coordinates. It's very easy. So this tells me that maybe I should be thinking of using cylindrical coordinates right here. So what we're going to do is we're going to convert everything to cylindrical. So remember our formulas. X equals r cosine theta, y equals r sine theta, and z is just going to stay z. Okay, so what does this thing become? Well, then xz, our integrand, that's what we call the thing that we're integrating, is going to become r cosine theta times, well, z stays z, so it's just z. Okay, so that's what this thing is going to become. So in our integral down here, we're going to have r cosine theta times z. All right. And now the dv. We should probably figure out what these things look like before we write down the r, dr, d theta, dz here, because sometimes we have to, as we saw in the last chapter, we have to reorganize those things. We have to write them in a different order. So we have to be careful about the order in which we integrate. So let's figure out what this region looks like. We said that x squared plus y squared equals 9 is a circle. So if I'm saying that it's less than or equal to 9, we're inside the circle. It's actually a disk. It's the interior of a circle of radius 3. Now, what does x squared plus y squared become when we use these coordinates? Well, x squared plus y squared is the same as r squared cosine squared theta plus r squared sine squared theta. I can factor out the r squared. And cosine squared plus sine squared we know is always equal to 1, right? So this is just r squared. So that's very nice. This just becomes r squared is less than or equal to 9. Or in other words, r is less than or equal to 3. So that is a good thing to recognize. This just becomes that. R is less than or equal to 3. Now, to say that x is greater than 0 and y is greater than 0, let's not substitute those in. Let's just think about that. We'll get back to that in a little bit. Z is just the z coordinate in cylindrical coordinates, so that's fine. Let's think about what this is saying. Let's draw the picture of what we're looking at here. X, y, z. Okay. R is less than or equal to 3. So we're inside, let me draw in a dashed line, the circle of radius 3. All right. We're inside this circle. That's what this is telling us. X is greater than 0 tells us that we are up here. We're in this part. We're at the positive x-axis. So we can ignore this back side of the circle, right? So we're really only looking at this front part up here. Those points in the back are not part of the region. And then what else do we have? We have y is greater than 0, greater than or equal to 0. So that means we can ignore this half of the circle over here where the negative y's live. So really all we're left with is just this part of the circle. And remember, r is less than or equal to 3, so we're actually inside the circle here. So we're actually in there. And then finally, z is going from 0 to 1. So we're going to start down here at 0 and we're going to go up to 1 on the z-axis. Right, so just lift all that up. This is the region that we're dealing with. So now let's see. We need to think about what this is in cylindrical coordinates. Well, r is going from 0 to 3. What's theta going from? Well, remember, theta starts here at the positive x-axis and then winds around counterclockwise. So we're going from theta equals 0 to here. That's 90 degrees. That's pi over 2 radians. So we see that theta here is going from 0 to pi over 2. And we were told, let me write down again the r. R is going from 0 to 3. And z is going from 0 to 1. Well, that's very simple, isn't it? Right? These are going to be our bounds here. Since these are all constants, it doesn't matter what order I write the dr, the d theta, and the dz. Okay? So let's put that volume element in here. So here's our volume element. We know that it's equal to r dr d theta dz. And like I said, I can write it dr d theta dz. I could even mix these up. I could write these in a different order. It's not going to matter. Now I put the bounds in. First integral on the inside is r. R, we said, went from 0 to 3. So here we are, 0 to 3. The next integral we do is theta. Theta, we said, went from 0 to pi over 2. So here we are, 0 pi over 2. The third integral is with respect to z. We said z went from 0 to 1. So there we are, 0 to 1. So that's what we've got. I could write this integrand here as r squared cosine theta is z. So let's think about it that way, since we have two r's in there. So now we have to do this integral. So first we're integrating with respect to r, so we're going to anti-differentiate r squared. We're treating theta and z as constants. So the antiderivative of r squared is 1/3 r cubed, right? So 1/3 r cubed cosine theta z. We're going to evaluate that from 0 to 3. And then we're going to integrate that answer according to what we had out there. Well, let's see. When r is 3, I get, I goofed. You were probably about to say something. Antiderivative of r squared is 1/3 r cubed. Okay, so when I plug in the 3, I get 27 divided by 3 is 9. When I plug in 0, I just get 0. So this thing is just 9 cosine theta times z. Okay, so moving along. Now we do the antiderivative with respect to theta. Antiderivative of cosine theta is sine theta. So what we have here is 9 sine theta times z evaluated from 0 to pi over 2. And then we'll integrate that when we're done evaluating it. When theta is pi over 2, sine of pi over 2 is 1. When theta is 0, sine of 0 is 0. So I'm going to take what I get when I plug in 1 up here and subtract 0. So that's just, I just get 9z. Finally, we do this integral. Antiderivative is 9 over 2z squared. Right? Evaluated from 0 to 1, we get 9/2. And so there's our final answer. Now we're dealing with cylindrical coordinates, so maybe we can use these to get a handle on this. Let me draw a picture of it, and I'm going to draw a picture of it. I'm going to draw a picture of it upside down. You don't have to do it this way, but I think it'll end up being easier if we do it this way. So here we have our cone. I'm going to put it centered right on the z-axis there. And the radius is going to be 2, and the height is 2, so this number is 2. So how do we get that volume? Well, what I'd like to do is find out what this region is in terms of cylindrical coordinates. Well, this is the z-axis. And if I just restrict myself to the yz plane, I'm just getting a diagonal line, right? And in fact, that's the equation z equals y. Okay, but in this plane, that's also, well, if I'm restricting myself to this plane, y is the same as r here, right? Because r is just the distance from the z-axis. And in this plane, so is y. So you can see that this line here is really given by z equals r. The height of this line is the same as the distance that line is from the z-axis. And I could have done the same thing on the x-axis. Right? That line coming out this way, when I restrict myself to the xz plane, x is the same as r. Right? The r is just the distance in that direction, and so is x. And so again, this line is just z equals r. And I think you can tell that as I spin around the cone is really given by the equation z equals r in any direction. If I just go out some distance in the r direction and go an equal distance up, if I make my z equal to r, I will land somewhere on this cone. Right? So the equation of this cone really is just very simple. It's just z equals r. Okay, so I think that's enough to figure this out. All right, so if we want to find the volume of something, remember what we do. We take the triple integral of 1 dv. that's going to be the volume. Okay? And so our region here is just that cone. All right, so let's figure out what these bounds are going to be. Let's set this up. R, dr, d theta, dz. What does R range from? Well, R starts at 0 and comes out until we hit the cone, right? But as we said, the cone is given by z equals R. So R goes from 0 to z. Whatever my height was, that's exactly how far I have to go out until I get to the cone. So R is going to span this entire distance here. What about my theta? Well, theta is how far I go around. Well, look, I went all the way around. I got a circle here. The top of the cone is a circle. So if I was doing half the cone, I would just do theta from 0 to pi. But I'm doing the whole cone, so I go from 0 all the way to 2 pi. And then what does z do? Well, the height of the cone is 2, so z goes from 0 to 2. All right, and that'll do it. So let's see what this comes out to be. I anti-differentiate this with respect to r, I get r. Evaluate from 0 to z, I get z, right? So this just becomes z. Oops, okay, hold on. I forgot about my r over here, right? It's not 1, it's 1 times r. So the this is an r, that simplifies to r. So the antiderivative is 1/2 r squared. Okay, I thought that was going to be too easy. So I evaluate that from 0 to z, I get 1/2 z squared. Okay. Almost forgot about that r. It's easy to do that, so be very careful about that. Now I anti-differentiate this with respect to theta. Well, that's just 1/2 z squared times theta. Evaluate that from 0 to 2 pi. It's just, you just multiply this by 2 pi, right? Because it doesn't depend on theta. So it's just pi z squared. Okay? Now in the last part, we're just anti-differentiating with respect to z. So that's 1/3 z cubed. Right, evaluated from 0 to 2. So that is pi over 3. 2 cubed is 8. And so, and then evaluated 0, you get 0. So this is just 8 pi over 3. I want to point out, though, that we could have done this a slightly different way. We didn't have to do dr, d theta, dz. You could have done dz, d theta, dr, or actually dz, dr, d theta. Either one of those would work. Let's do this integral dz, dr, d theta. Okay, how would I set it up this way? Well, here my first integral on the inside is a z. So I'm asking, what does z go from and to? Well, let's look at the picture. Z doesn't start at 0, right? That's outside the cone. I'm not at the cone yet. I'm going up and up and up and up and up and up and up until I hit the cone. Now at that point, z is equal to r. So z starts at r. And then how high does z go? Well, z goes as high as 2, right? It goes to the top of this cone. So if I set the integral up this way, I would go from r to 2. Now what does r go from? R starts at the center and goes all the way out to the edge of the cone, right? So if I'm at the center, z is going to go from 0 to 2. If I'm halfway out, z is going to go from here to 2. If I'm all the way out, z is going to go from 2 to 2. All right, so r goes from 0 to 2. And then theta, as before, takes me all the way around the cone, so it goes from 0 to 2 pi. So notice it looks a little bit different, but this is how you'd set it up if you reversed the dz and the dr. Okay, and go ahead and work it out. Make sure, homework exercise there. Make sure it also gets you to 8 pi over 3. It should.